Welcome to lecture number 6. In our previous lecture, I have discussed the network theorem problem, basically superposition theorem and Norton's theorem using AC sources. So now today I will discuss at first the Thevenin's theorem, how to solve a network problem using Thevenin's theorem with the AC sources. Okay, so this is lecture number 6. So at first I will consider the same problem which I have considered before for solving the superposition theorem or Norton's theorem. So that is, this is the AC voltage source. With this there is a resistance 4 ohm connected in series, and with this is one inductance J5 ohm, and this is the capacitance, that is minus J2 ohm, and here is the current source. So the value of current source is 2 at an angle 0 degree, and the voltage source is 5 at an angle 0 degree. It is in volt, it is in ampere. So now we have to find the current through this J5 ohm impedance. So these are mainly the load impedance. Okay, this is the mainly load impedance. So we are considering about Thevenin's theorem. So the step 1 for Thevenin's theorem is the load impedance path is removed by a short circuit, by a open circuit. Okay, so if I redraw the circuit again, so step 1, so this is the AC voltage source and resistance, and this part will be open circuit, and the remaining part are as it is same. So now we have to find the open circuit voltage, that is VTH or VOC at that open circuit terminal. So this voltage is known as the Thevenin or V open circuit. Okay, so this is 5 at an angle 0, 4 ohm minus J2 ohm and 2 at an angle 0. So now the current 2 at an angle 0, it is flowing from this side. Actually it is flowing from this side. So I want to find out the voltage in this terminal across AB. Okay, so across AB terminal the VTH will be 5 at an angle 0 minus V minus I into R. This IR drop, and what is the I? Look, the current 2 at an angle 0 is flowing from right side to left side. That means if I consider the from 5 at an angle 0 side, that means the supply volt side. So that means with respect to this side the current is negative. The current is flowing from the right side, that means 2 at an angle 0 side. So from here it is flowing from right to left. But if I look from this 5 at an angle 0 supply voltage side, the current is negative. So that means here the voltage drop across the 4 ohm means 4 into minus 2 at an angle 0, right? So actually we get 5 at an angle 0 plus 8 at an angle 0, that means 13 at an angle 0 volt. So this is the Thevenin equivalent voltage or VTH. Okay, so step 2, the step 2 is to find the Thevenin equivalent impedance, that is ZTH. So to find the ZTH, all the voltage source is replaced by the short circuit and the current source is replaced by the open circuit. So now if I redraw the figure again, the supply voltage side is replaced by the short circuit. Here is the resistance, and here is the basically load impedance, and here is one capacitance, and this side is open circuited. So this is the 4 ohm. So now I want to calculate the ZTH. So to find the ZTH, consider a fictitious voltage source across this open circuited terminal. Okay, across this terminal. So with respect to this terminal, if I connect a fictitious voltage source here, the current is flowing from the supply volt towards the 4 ohm resistance. Because if I apply KCL across this node, the current is flowing from this fictitious supply voltage. So from this node, it will divide across the 4 ohm resistance and across this capacitance minus J2 ohm. But as this side is open circuited, so no current is flowing through this capacitance. The entire current will flow through this 4 ohm resistance. That means there is only 4 ohm resistance is present, and the J2 ohm capacitance is here irrelevant. So that is your ZTH is only 4 ohm here. Okay, clear? Next thing is to find the current through this load impedance terminal, that means the J5 ohm terminal. So the step 3, will be the current. So the formula is exactly similar, that is IL equal to VTH by ZTH plus ZL. So ZTH is 4 ohm, VTH is calculated 13 at an angle 0 volt, and ZL is given J5 ohm. So now put the value. So it is 13 at an angle 0 divided by 4 plus J5, ZL is J5. So if I calculate, IL will be 13 at an angle 0 and 4 plus J5 means it is 6.403 at an angle 51.34 degree. So again the value will be, so the real part by real part, so that is 2.0t, and the angle will subtract because this is a divide case. So that means the angle is minus 51.34 degree. So this is your IL using the Thevenin's theorem flowing through the load impedance path, that is J5 ohm. Clear? So this is all about the Thevenin's theorem. So now if I check it using a simulation, so what we will check? So look. So now this is the same circuit which I have already drawn it in MATLAB simulation software. So actually this circuit I have discussed before in my previous lecture already, so I am not going to the very much details in this lecture. So this is the voltage, AC voltage source, and this is the current source, and the value of the inductance and the capacitance will be calculated by this method, which is already mentioned here and I have already discussed. Okay, so now if I run the simulation, I will find the current through this inductive reactance or inductance part, that is mainly our load impedance. Okay, so if I run the simulation, so here it is actually showing the same value which I have calculated just before. The current is 2.03 and at an angle minus 51.34 degree. So that means your theoretical calculation and simulation result will be exactly same, and again it is proved. Okay, so that is basically the all about Thevenin's theorem. So now the next part will be the maximum power transfer theorem. Okay, maximum power transfer theorem. So in the previous lecture of DC network theorem, I have already shown that what is the condition of maximum power in case of using DC source. The condition will be RL, that means load resistance, is equal to the Thevenin equivalent resistance, RTH. Then this is the condition for to get maximum power from a circuit when the load resistance is equal to the Thevenin resistance. So now in this case, if I use the AC voltage source, so what will be the condition? Okay, so now I have to check it. So if the circuit, I draw the circuit, this is the AC voltage source, and with this this is the series impedance, okay, not resistance only, this series impedance, that means it is a combination of resistance and inductance, and here it is the load resistance and load inductance, so that means the total thing is that load impedance, okay. So now, so suppose this is the supply voltage Vs and this is Rs, the series resistance, and this is Jxs, this is RL and Jxl, and the current flowing through this supply voltage, this is I. So now the total circuit impedance is the total impedance that is Rs plus Jxs plus RL plus Jxl, that means the Z equal to basically Zs plus Zl. So we can rearrange it by Rs plus RL plus J within common Xs plus XL. So this is basically the total impedance occurred by the circuit. So now what is the current? The circuit current, supply current. Supply current is the total supply voltage Vs divided by the Z. The Z means it is under root Rs plus RL whole square plus Xs plus XL whole square. So this is the current, the supply current, the supply voltage by the total impedance. So now the power delivered to the load, that is PL. So that is I square into RL, the power delivered to the load, and if I put the value, I square means Vs square divided by the total thing, but the square root will be omitted, that is Rs plus RL whole square plus Xs plus XL whole square into RL. So this is basically the I square into RL. So now in this case, basically here I can consider the two cases. The first case is the load. Basically the load consists of the variable resistance and variable inductance. So first case, the case 1 will be variable reactance and fixed resistance. The first case is variable reactance, that means in load variable reactance and fixed resistance. So now since the RL is fixed and XL is variable, that means RL is fixed and XL is variable. Okay, so the maximum power transfer, the occurring maximum power, the condition will be, to get the maximum value, what we can do? Simply derivative the maximum power with respect to the, what is the variable quantity here? XL, that means dP dXL, because RL is fixed. Now in this case the variable quantity is inductive reactance, that means XL, so dP dXL and is equal to 0 to get the maximum power. This is the condition. Okay, so now so if we solve the thing, that means ddxl of, write the value of P, that is Vs square into RL divided by Rs plus RL whole square plus XL plus XL whole square. the whole thing is equal to 0. So by solving this, simply the derivative action will here nothing else, simple derivative action. So by solving this, we can write minus 2 xl plus xs, that is equal to 0, and therefore xl equal to minus xs. Okay. Therefore, the maximum power transfer, the reactance of the load is exactly same as the magnitude of the source in the network, but is opposite sign. That means the source reactance is exactly similar with the load reactance, but in opposite sign. So this is the condition for getting the maximum power when the load resistance is fixed and load reactance is variable. So this is the condition for the case 1, right? So now the second case. Case 2 means the load reactance is fixed here. That means load reactance is fixed but load resistance is variable, and load resistance is variable. That means RL here variable and XL is fixed. So now to get the maximum power, so same thing we can do. That means dP, here the variable term is the load resistance. That means dP dRL equal to 0. Look, the previous case XL is variable, so we get the derivative of dP dXL, and now RL is variable, so the derivative will be dP dRL. Okay, that is equal to 0. So if I simply put the value, that means d dRL of Vs square into RL divided by Rs plus RL whole square plus Xs plus XL whole square, that is equal to 0. So now with respect to RL, that means Rs plus RL whole square plus Xs plus XL whole square minus, that means V into U dash d dRL of RL means 1 minus RL into 2i's of Rs plus RL. Okay, simply U by V, the format of derivative. Okay, so next from this thing we can write after solving, that is Rs square plus XL plus XL plus XS whole square minus RL square, that is equal to 0, right? The other term will be cancelled out. So now we can write RL square equal to Rs square plus XS plus XL whole square. So now your RL, that is load resistance, will be square root of Rs square plus XS plus XL whole square. So this is the condition for maximum power transfer when the load resistance is variable but the load reactance is fixed. So this is the condition for the second case. So now the case 3, the third case and the final case. That means the load is such that both resistance and reactance will be variable. Okay. So if I go to the third case, that means from the case 1, that means when the load reactance is variable, we get that XL equal to minus XS. So the power will be IL square RL, that means VS square RL divided by RS plus RL whole square plus XL plus XS whole square. This is the general formula of power. So from case 1 we get XL equal to minus XS. So by putting this we get P is equal to VS square RL by RS plus RL whole square. And from the case 2, what we can write? RS equal to RL. Okay, because we have already calculated in our DC network theorem DC network theorem lecture series. So that is dP drl equal to 0. So that is RS equal to RL. Okay, so by substituting again, we get that the P is equal to Vs square by RS equal to RL. Here put it, that means Vs square by 4RL. So actually from this condition XL equal to minus XS, it is obtained from the case 1, that means when the only load reactance is variable and load resistance is fixed, and case 2 is the load resistance is variable, load reactance is fixed, that means RL is here variable quantity. So by combining these two cases, case 1 and case 2, that means the load resistance and load reactance both are variable, we get the maximum power. So actually it is the P max here, right? Maximum power will be, by putting these two conditions, we get Vs square by 4RL. It is exactly the same. It is exactly same as the DC network theorem, right? So that means it is said that if the load is such that both resistance and reactance are variable, maximum power would be delivered when both resistance and reactance are variable. Okay, the maximum power will be delivered when the condition is ZL, that means load impedance, is equal to the complex conjugate of source impedance. ZL equal to ZS star, that means here it can be written as complex conjugate. Complex conjugate means RS equal to RL and XS equal to minus XL. Here the term minus, so it is defined as complex conjugate, right? So this is the main condition of maximum power transfer theorem using AC source. So then what is the main statement? That means the power delivered by a active network to a load connected in the circuit across the load terminal is maximum when the load impedance is the complex conjugate of the source impedance. It means that load impedance is equal to the complex conjugate of source impedance. So it is the final criteria for maximum power transfer theorem using a AC supply voltage. Okay, so by combining the load resistance is variable and load reactance is variable, by combining the two cases we can achieve the final criteria for the maximum power transfer theorem. So nothing else. So now if I consider the same problem here, okay, in our previous problem we get that, so the problem is same, that is if I go to the next page, the problem is this is the supply voltage and resistance here, and here is inductance, and this is the capacitance, and this is the current source, right? So it was a problem that is 2 at an angle 0 ampere and it is 5 at an angle 0 volt. This is 4 ohm, this is J5 ohm, this is minus 2 J ohm. So the if I can find the maximum power, so the steps are exactly similar as the Thevenin's theorem. It is actually similar with the DC Network theorem also. Okay, so right. So now the maximum power will be VL square by 4RL. That means the VTH square, actually VTH square by 4RL. So what is the VTH? That is, we have calculated 13 angle 0 by 4RL. RL means actually it is the ZTH. Actually this is the AC network theorem, that is ZL equal to ZTH. So what is your ZTH? ZTH equal to 4 ohm. We have already calculated in the Thevenin network theorem. ZTH equal to 4 ohm. So actually you can replace it by ZTH. So 13 angle 0 whole square by ZTH. 4 into 4. 4 into ZTH means 4 into 4. So that means 169 by 60. So your P max will be 10.5625 watt. That means the procedure for finding the VTH and ZTH are exactly similar as the Thevenin's theorem. First, if there is a problem to solve with the maximum power transfer theorem, first the step 1 and step 2 are exactly similar of Thevenin's theorem. That means to find the Thevenin equivalent voltage and to find the Thevenin equivalent impedance, VTH and ZTH. So once you have found the value of VTH and ZTH, then and there you can go for the calculation of maximum power. So the formula is VTH square by 4 ZTH. So here VTH and ZTH I have calculated in previous problem, that means using Thevenin theorem. So now put the value of the VTH and ZTH and simply get the maximum power 10.5625 watt. So now again I will check the value of the maximum power in simulation, right? So look, so here this is the same problem. So now actually we can find the maximum power across the load terminal. So here it is, this terminal is basically the load terminal here. So now I have connected a voltmeter across this load terminal to get the load voltage, and it is the ammeter connected in series with the load impedance to get the load current. So basically the load power will be the product of load voltage and load current. So here we can find only the active power, because maximum power transfer means the active power delivered to the load is maximum when the condition is ZL equal to ZTH. So now here is the load impedance, that is the J5 ohm. So now to get the maximum power, we will substitute the value of ZTH in place of ZL. So now ZTH is 4 ohm. So now we can replace the ZL by the simply ZTH, that is equal to 4 ohm. And across this load terminal the voltage and current will be measured, and by the product we can get the P means active power and Q means reactive power. So here if I run the simulation, so look, the active power is 10.56 watt. It is exactly similar by our theoretical calculation, and the reactive power is 0. So it is the same thing. So now if I change the value of the ZTH, so if I put 8 ohm, suppose for an example, the ZTH will be 8 ohm. So now if I run the simulation, look, you will get the P is 9.389. It is less than the maximum power 10.56. So now if you want, so you can put the value of suppose here 8 ohm the load resistance is 8 ohm and the load reactance is J5 ohm. So now check the various condition you can put here and check the maximum power, whether it is maximum or not. So again you will get the maximum active power is 5 watt and reactive power is 5 var. So it is not the maximum condition. So that means the conclusion is the maximum condition is obtained if and only if we put the load impedance is exactly the same of the load source impedance, the Thevenin's equivalent impedance, that is the 4 ohm. So if I put the 4 here, then only we can get the maximum power across the load terminal, that is 10.56 watt. Okay, so this is all about the maximum power transfer theorem, and these are the two cases of proving what is the maximum condition to get the maximum power from the circuit using AC voltage source. Okay, so this is all about the today's lecture. So with this I am ending the AC network theorem. Okay.